With no ado, I'd like to introduce Joshua again. Joshua is a professor at Queen's University, and is going to talk on solar photovoltaic. Thanks very much.
Actually, it was really good that Jeremy went first. Before you even consider the smallest solar cell panels, installation in your home, or wind, efficiency has to be done. And he talked about some of the bigger things, like, say, replacing your furnace, which would represent a major expense. There's also little things that you can do to make significant decreases in the amount of electrical energy that you use. A good investment for everybody, if you don't have one now, is a watt meter. You can buy a little kilowatt meter for like $50 on the internet. And it's essentially just a meter that you plug into the wall and then plug your appliance in through it. And you get an immediate feel for how much power it's drawing, how much energy it uses over time. So if you're thinking about putting solar or wind in your home, one of the first things you want to do is absolutely minimize the amount of electrical energy you're using. So you can do that to all your major appliances, your freezer, your refrigerator, and immediately can make it possible for you to make calculations on whether or not it's time to replace them. At the same time, and this is something that is missed by almost everybody, except for the off-the-grid people, is phantom loads. Most of the electrical appliances that you use now, when you plug them into the wall, even if they're not on, even if you're not using them, they draw some power. And that power adds up over time. So I've, for instance, seen gaming systems that will use 13 watts when you're playing Battleship Galactica or whatever, and 12 watts when it's off. It's almost the same. It's drawing electricity every day, day in, day out. And all of that adds up. And so you can cut the energy use in your home by at least 10% for the average home in Canada, the US now, just simply by unplugging or putting the devices in your house that do draw power when they're not on like a power strip. So power strips are relatively inexpensive. You can get the fancy ones to do like your printer and computer, and it will make it so that when you shut your computer off, it automatically turns off all the peripherals. Those things are excellent investments, very high rates of return, and make it much easier to do something like power your entire house with solar cells. So what I'm going to go through today is just an introduction to the technology. Everybody's probably already familiar with it. Then talk a little bit about the nitty-gritty. Photovoltaic science and engineering have progressed very quickly in the last few years, and now you've got some products that you might actually consider putting in your home, how to actually install them, and how to get your project done. And then finally, I'll end with a case study that you heard a little bit if you came to the first session, the cost calculations, and then we'll have time for questions. So first, photovoltaics is just a fancy way of saying we're taking sunlight and turning it directly into electricity. They're solid-state devices, so the only thing moving in them is electrons. And they've done everything from powering satellites. You probably have some little household gadgets that run off of them. And we're starting to see them more and more. So any off-grid application, solar cells are one of the best ways to provide power for it. So you see it a lot for, say, road construction or the powered signs along the highway. In Indiana, I know where we have lots of deer trouble. They put up solar-powered little things that would give warning flashes and lights if a deer crossed onto the highway. And the reason they did that was not because they were particularly green. It was just the best, most cost-effective way to produce power when you're off the grid. Now, is anybody here in an off-the-grid home? So all of you are on the grid, which makes it more challenging economically. And all the economic figures I'm going to give you today are for what is possible today. But all of those figures are going to change within the next month or so when the Ontario government finally gets its act together and puts forward another renewable energy standard offer program. We don't know exactly what that is going to be, but we do know it's going to be better than what we have now. So the reason that I do photovoltaic research at Queen's, my PhD was in it. That's what I've sort of dedicated my life to. And the reason that I did that is, to me, it's the most promising means of providing the energy that we need to maintain our standard of living, our lifestyle. We've got to get off of coal and natural gas and oil, and this is a technically feasible way to do it. So the way... Can you talk a little bit louder? Sure. Really hard to understand. Sorry about that. Talk much louder. All right. So the way a photovoltaic system works is sunlight hits the panels, it's absorbed. Depending upon the efficiency of the panel, I would say that the standard cell would produce between 10 and 20% of that sunlight turned directly into DC electricity. DC electricity is like what you are pulled from a battery to run off a children's toy. Normally, if we're going to be on the grid, it runs it through an inverter, which turns the DC into AC. AC is exactly what you get out of the wall of your house. That power can be used directly in running your dishwasher, your television, whatever, however you're going to use it. Or it can go through a breaker box, literally spin a utility meter backwards, and push the electricity onto the grid. And a lot of people are interested in this because if you purposely oversize your system so that you're constantly giving electricity to the grid whenever sunlight is shining, you literally pull in checks from the utilities. And in Ontario, we have this spectacular program right now. It's a 42-cent per kilowatt-hour feed-in tariff where they actually pay you for generating solar energy. The only drawback is they want you to keep 2 meters. So you have 1 meter for the amount of power that you buy from the utility, and the other one is what you're pushing back onto the grid. So you're essentially using the grid as a large storage battery for yourself. And this will work up until the point where we have about 15 to 25% of the grid covered by solar. Once it gets to that point, then people like me can worry about how we're going to move beyond that. But for where we are right now, where it's much less than 1%, everybody in this room, everybody in Kingston could go solar, and we would not hurt the utilities in any way, shape, or form. So there's essentially 3 types of photovoltaic materials on the market now that make up the vast majority, over 90%. They're all based on silicon. It's the same material that is used to make, say, Intel penny chips. The most popular are crystal silicon cells, and these generally come out in wafer form, and they either look, on the panels, will either look circular or slightly squarish. They have the highest efficiencies. They're the ones that are pushing over 20%. And when you think about solar, many people are just like think that the most efficient is what matters, and that's not true. We have solar panels now, like triple junction, made out of gallium and indium, that can push over 40%. But you will never afford that for your home. It works great for NASA. It works great for doing some sort of military thing, but it doesn't make sense economically for you. Silicon is an extremely abundant element, relatively inexpensive to process, and because of that, they're currently the most economical ways to do it. So for crystal silicon, it has good efficiencies. It's relatively well-established technology. We already know how to work with it because of the semiconductor industry, and it's stable. Its performance, when you buy a panel, you stick it in the sun, it will essentially stay that same efficiency throughout its warranted lifetime. Polycrystal silicon, of which there's a panel out in the hallway as an example, is almost as good as crystal silicon. You can see the individual crystal sections in it, and as you butt 2 crystals next to each other, that sort of boundary layer between them has electronic defect states, which scavenge a few of your electrons, so the efficiencies aren't quite as high. And so you might see efficiencies around 14, 15, 16%. And again, it's a relatively well-established technology. Most of the panels that you will get on the market now are one of these 2 things. Most of the major producers of solar cells specialize in these types of panels. Now, the disadvantages of both of these types are they're relatively expensive to produce as compared to what the new players on the market are. They have a low absorption coefficient, which means you need a pretty thick layer in order to be able to absorb all the sunlight, thus driving up your costs. And because you need a thicker layer, you need a large amount of highly purified feedstocks. And until this year, we had a big problem in the solar industry. Because of feed-in tariffs in Germany and Japan and other places in Europe, the supply was not keeping up with the demand for solar. And so we've seen for year after year after year, the price of solar cells would drop as we increased the production, the same way it did in the computer industry. And then a couple years ago, it started turning over and actually increased a little bit. And so now we're starting back down that curve, but it's kind of like a fall of our own success. It grew so quickly, a lot of the chemical firms that produced the pure silicon for the solar industries just couldn't make it up. And so as they saw this incredible demand develop, now everybody in the world, every chemical company that you can name is trying to make highly purified silicon for the solar industry. And so we finally are out of sort of this dearth in supply, and things are starting to move forward again.